Okay, so that's a little teaser, but in order to understand these finite fields of non-prime size, interestingly, you have to start talking about polynomials. So we're going to switch to talking about polynomials now. You have to at least understand univariate polynomials, one variable polynomials. Yeah. Okay, so let's talk about univariate polynomials. Okay, and remember our notation here. If f is a field and x is a symbol, then this f square brackets x means all the polynomials with coefficients in this field, over variable x. Okay, and as I said before, for now, you should just think about polynomials symbolically. Later, we'll actually talk about plugging numbers into polynomials. Let me also mention a fact that I guess you know. This number n is called the degree of the polynomial, well, assuming Cn is not 0. Okay? All polynomials have a degree, except for the constantly 0 polynomial. That has no well-defined degree. You can just leave it undefined, or maybe call it negative infinity or something. But the all zeros polynomial is always like a special case. Okay, but if the constant coefficient is like 3, the polynomial that just has constant coefficient of 3, that's a polynomial of degree 0. Okay, now this set of polynomials is actually not a field. Because in general, polynomials don't have reciprocals. They do have plus, minus, and times, though, which means that the math people would call them a ring. So just like the integers, they can at least support plus, minus, and times. And in fact, there's many, many analogies between the set of univariate polynomials over a field and the set of integers. They share many properties. So actually, I'll just mention some of these properties briefly. First of all, a fact is that there is some notion of division for univariate polynomials. But it's just like the notion of division for integers, where you have a quotient and a remainder. Okay, so if you have a polynomial b of x, you can divide it by a of x. And you'll get some other polynomial q of x, which is the quotient. And a remainder, r of x. And the property of the remainder is that it's, quote unquote, smaller than the thing you're dividing by. So the degree of r is less than the degree of a, always. Okay, and what this means is, well, that b of x is a of x times q of x plus r of x. And I guess probably in some math course, you've probably even seen the algorithm for this, like polynomial division. I mean, it's like the usual division algorithm somehow. Sometimes it's called synthetic division or something. But that's an important property of polynomials, that this notion of division makes sense with a remainder which is smaller than the thing you're dividing by. And actually, one consequence of that is that Euclid's algorithm also makes perfect sense for polynomials over a field. And you could do Euclid's algorithm to compute like the greatest common divisor of two polynomials, where greatest is with respect to degree. And you can also try to factorize polynomials, just like you try to factorize integers, where like you take the thing and see if there's like you can write it as a product in a non-trivial way, meaning a product of two things that have degree bigger than 0. And if you cannot write a polynomial as a product of two things of smaller degree, then you call that polynomial a prime. Or the preferred terminology, I guess, is irreducible. But you can also call it prime if you like. So let me put this up as a definition. A polynomial p of x is irreducible or prime if it can't be factored as the product of two lower degree polynomials. And also, I guess, like with prime numbers, and it should have degree at least 2. OK, and just as we saw before, if you take the integers mod a prime, you get a field. If you take the polynomials mod a prime polynomial, you also get a field. And the proof is like literally exactly the same. It's the same like GCD Euclid's algorithm business. So let me write that. Because this sort of tells you, in some sense, what these fields are. The set of all polynomials, f of x, mod p of x, is a field of size cardinality of the coefficient field f to the power degree of p if p is polynomial prime or irreducible. OK, and what does this mean? Same thing with integers, right? You have all the polynomials, but you like kind of treat p of x equals 0 as like a formal rule. So if you ever have like a polynomial which is a multiple of p of x, you're like, oh, this is just 0. And so you can like start subtracting away multiples of p of x from any polynomial, and it's like the same mod p. In particular, it's not hard to show that you can keep doing this. Given any polynomial of any degree, you can like start subtracting away multiples of p of x to kind of make the degree go down until the degree of your starting polynomial is less than the degree of p. Then you can no longer like take multiples of p to like cancel out the high degree terms. So in particular, like this set is like all the polynomials of degree less than the degree of p. And that's why, I mean, these are representatives for the set. And that's why the number of elements in this set is size of f to the degree of p, right? Because that's the number of polynomials. That's the number of way of choosing coefficients for each possible power of the indeterminate x up to degree p minus 1. And similarly to the integers mod a prime, right? I mean, if you just add two representatives together, you don't have to do anything special. But when you multiply two of them together, you could get something that's of degree bigger than the degree of p. And then you have to like subtract off some like multiples of p to make it go down to degree less than the degree of p. So sort of just like with the integers. Good. So actually, whenever you have a field f and an irreducible polynomial, which is like a prime, you can make a field of this f to the degree. And as we'll see in a minute, for every degree L, there's always at least one irreducible of degree L. And that implies the existence of all these fields. Okay, the fact that they're like unique and that you effectively get the same field if you use different irreducibles is, a much harder theorem, but you can just take it as a fact. So, as an example of this, let's consider the field to be f3, the integers mod 3. And then you can check that this polynomial, x squared plus 1, is irreducible in f3. you just like can brute force check that there's like no two polynomials, like linear polynomials, mod 3 that multiply to this guy. I mean, there's only, I don't know, 9 polynomials of degree up to 1. So you can just try multiplying them all together and see that none of them equals this. Okay, and therefore, by this theorem, the set of all polynomials, sort of mod x squared plus 1, is a field. Well, it's F9. Right? This is all the things that look like a plus bx, subject to the rule x squared plus 1 equals 0. And this rule comes in when you like multiply two of them together. You can always consider x squared plus 1 equals 0. Actually, computationally, an easier way to do that is to always consider x squared equal to minus 1. So wherever you see an x squared, you're just like, oh, I'm going to turn this into a minus 1. And that's how you reduce degrees back down to linear, or to at most 2. You cancel out all x squareds like this. And as you can see, this is exactly the same thing I told you before, where I told you, oh, it's like a plus b times I. I mean, here it's just, there we called I the number whose square is minus 1. And like here we're calling x the symbol whose square is minus 1. But it's the same thing. OK, and this fact that I used to show that it doesn't work mod 5 is because x squared plus 1 is not irreducible mod 5. Because 1 plus 2x times 1 plus 3x is a factorization of x squared plus 1 mod 5. OK, so as a corollary of knowing this, we have a similar situation where if you're somehow given an irreducible polynomial of degree L, mod P, you can do arithmetic in this field Fp to L. It's doable efficiently in like L, polynomial and L log P time. OK, so to write down like one field element, you have to write down all the coefficients for degree 0 up to degree L minus 1. So it's like L numbers, and each of them is a number mod P, so it's like log P bits. So you basically need like L log P bits to write down a field element. OK, and then addition is basically vector addition mod P, and subtraction. And for multiplication and especially division, you need like Euclid's algorithm to compute inverses. OK, any questions about this? Yeah. Great. So the question was, are there efficient algorithms for checking irreducibility? Yes, there is. That's great. So let's just exactly return to this question. How do you get like degree L irreducible mod P? OK, let's assume you know P and you know P is a prime, and you're like, oh, I wish I had this field of size P to the L, so I have this target number L. And now you want like a degree L irreducible mod P. You can actually do the exact same thing. So you can pick a random polynomial of degree less than L just by picking all its coefficients uniformly at random. And then you want to check if it's irreducible. And luckily, there's an efficient algorithm for this. Yeah, I forget who it's due to, but it's definitely much older than the primality testing algorithm. So this is doable in poly L log P time. deterministically. Maybe it's due to Shoup? No, well, I'm not sure who it's due to. But it's easier. And in fact, all the algorithms for polynomials are easier than their algorithms for integer analogs. So for example, it's a famous open problem whether you can factor integers efficiently, but you can factor polynomials efficiently. This is a famous result of Berlekamp from like 60s. It's actually a randomized algorithm. We don't know how to de-randomize it. But you're given any univariate polynomial over a field FQ, Berlekamp's algorithm factorizes it efficiently. So particularly that tells you, it can tell if it's irreducible or not. But as I said, Berlekamp's algorithm is randomized, and if you just want to know if it's irreducible or not, there's a deterministic algorithm for that. Great. So then you might need to know, what about, is there like a prime number theorem for irreducibles? Yes, there is. And it's easier. It's much easier than the one for numbers. Okay, it's not called the irreducible theorem, but anyway, it's like the prime number theorem for irreducibles. And it says exactly the probability of this random polynomial is irreducible is between 1 over 2L and 1 over L for any P and for any L. Okay, and that's great. So it means, again, like if you just pick a random polynomial after like order L trials, you'll get an irreducible with high probability. And it's actually asymptotic to 1 over L, if you care about the exact constant. So that's great. But it's actually even better because okay, so it's again true that there's no known efficient deterministic algorithm for finding a degree L irreducible mod of prime. There's an efficient randomized algorithm. But there is an efficient deterministic algorithm. Well, it's efficient as a function of L, but not as a function of P. But that's often good enough. So this is the theorem of Shoup. There exists a poly L and P, not log P, but just P, time deterministic algorithm to get an irreducible in FPX of degree L. I should mention, by the way, this in particular proves that like an irreducible of degree L always exists. So this is not, as I said, fully efficient in the sense that it's not polynomial in L and log P, but often you only care about P being a constant, particularly 2. Okay, so often you're like, I want like a field of exponential size. I'll just try to get the one of size 2 to the L. That's very convenient. And then P is 2, so it doesn't matter if this is P or log P. It's a poly L time algorithm. It's deterministic, and it gets you an irreducible mod 2 of degree L. Okay, and so that's super great. That's all you would want in life. And it's actually quite nice, by the way. I mean, this mod 2 version, the elements of this field F2 to the L. Okay, on one hand, you think of them as polynomials of degree L minus 1, whose coefficients are numbers mod 2. Well, those are just bits, 0 and 1. So the field elements are just bit strings of length L. And to add 2 field elements, you just add these bit strings mod 2, which is great, and same with subtraction. Well, how you multiply them is more complicated, but they have some nice properties. Finally, let me just mention this last fact because I like it. If you're like, well, it's too complicated for me to go into like Shoup's book and like look up this algorithm, I wish it was even simpler, then you're kind of in luck. There's this theorem of Van Lint, which gives you super explicit irreducibles, but not of every degree, just 1/3 of the degrees. So Van Lint showed that x squared plus x plus 1 is irreducible mod 2. Let me just write this, irreducible in f2x. And also x to the 6th plus x cubed plus 1, and x to the 18 plus x to the 9 plus 1, etc. So you just proved as a theorem all these things that look like, 1 plus x to a power of 3 plus x to the twice that power of 3, they're all irreducible. OK, so if you're not super picky about the degree and you're willing to change the degree L by a factor of up to 3, then you can just take one of these as your irreducible.